Okay friends, so today we are going to see design of C clamp or the offset link. In this C clamp, as the name suggests, the link is just having a shape as a C, or sometimes it is also called as a G clamp. Or if you look at this, so this is again used to carry the maximum time. So tensile load or the tensile stresses are induced because at this particular point and at this particular point a tensile load is being applied. So most of the time the clamping devices which are used, these are the C clamps, these are called as the C clamps. And if you look at, if the load is applied at this point, so this load is eccentric, or this is load is offset to the main link, and that's why it is many times called as an offset link. Okay, so design of C clamp or offset link, if you look at the diagram, so you can see this is a sketch for the C clamp, and here the main link is over here, and here we are considering that it is having a rectangular cross section. Not necessary that it should always have a rectangular cross section. Sometimes it may have a I section, or sometimes it may be having a circular section, but here we are considering that it is having a rectangular cross section, and the load W is applied at this point. So these points where the load is applied is eccentric or is being offsetted by distance E from the main link or from the axis of the main link. So now we will begin the design of this C clamp link. So let W is the load applied, and the type of this load is nothing but tensile load applied on the C clamp. Okay, and E is offset distance between load point and axis of link. Okay, and B is width of the link, and T is thickness. And here we are assuming sigma max or sigma T is a maximum permissible tensile stress. Okay, so these are the assumptions we are making. Now if we look at this link, then this link may there are the direct tensile forces or tensile stresses acted, imparted on this link, and because of that we have to first of all find out the failure, or we have to first of all check the failure of the link because of the direct tensile forces. So first of all we will consider failure because of direct tensile stress. Now what is the load acted? Load applied is W, and the cross sectional area. So resisting cross sectional area is nothing but this is the resisting cross sectional area, which we can say width into thickness. So I can write resisting area, I will say A1, and this is equal to B into T. Okay, so I can write it down like this, 3B into T, assuming B is equal to 3T. Okay, so if the relation between the thickness and the width is not given, you may assume it that width is equal to thrice the thickness. Otherwise, many times in problem, this relation between the thickness and the width may be given. Okay, so assuming B is equal to 3T, so I can say this is equal to 3T square, and thus we know tensile stress is equal to load W divided by cross sectional area or the resisting area, and that's why we can say sigma T is equal to W upon 3T square sigma T. I call this as equation 1. Now, secondly, as we are seeing over here, this load is being eccentric. This load is eccentric, and because of this, there may be a bending. There may be a bending, okay, on this link. So, for that, again, we are going to find out the failure in bending. So, second failure because of bending. Now failure because of bending. So for that, what we have to find out? First of all, bending moment. So we know bending moment M is equal to nothing but load multiplied by the distance. So distance is nothing but eccentric, that is the offset distance, that is W into E. So this is a bending moment, and section modulus is equal to, that is Z equal to, what is the section modulus? Yes, the section modulus is T into B square divided by 6. So from this we can say T multiplied by 3 into T square divided by 6. So this turns out to be 9T cube divided by 6, and we can say Z is equal to 1.5 T cube. Okay, so if we know the section modulus, if we know the bending moment, we can find out maximum bending stress sigma B, and this sigma B is equal to M by Z, that is bending moment divided by section modulus. So M as it is nothing but W into E divided by 1.5 T cube. This is sigma B. We will call this equation as equation 2. Okay, so now on the link there are two stresses develop. One is because of the direct tensile stresses and another is a bending stresses. So we can say the effective stresses or the maximum stresses. Third, or that is the maximum stresses on the link, and this is given as, we can say, sigma max is equal to sigma T plus sigma B. Okay, that is direct tensile stresses and the bending stresses. So sigma max is equal to sigma T from equation 1. What is this sigma T? W divided by 3T square. W divided by 3T square plus sigma B. This is W into E divided by 1.5 T cube. Okay, so if you look at this equation, sigma max is must be given, that is the permissible tensile stresses, W that is the load, E is the eccentricity. So from this we can find out the unknown. What is the unknown? What is unknown over here? That is T. So we will get the cubic equation, and this cubic equation, after solving this cubic equation, you can determine the value of T, thickness. So from this we can determine value of T, that is thickness of the link. So if we get the thickness, we know the relation between the thickness and the width, that is width is equal to 3T, thrice T, and that's why we can find out the value of width also. And in this way we completed the design of the C clamp, or the same procedure may be adopted for the offset link also.